Hello. Hi. I am in charge mode CW152. Could someone please come help me? Because I'm using Teams to get using the visualizer, and it doesn't seem to be connected. So if someone please can have a look at this. CBX086. Yeah, 086. Sidani, SAIDANI.
Hi, Masood. We can hear now.
Yes, just 152. Thank you. Yeah, it's not connecting to Teams. You see, I'm using Teams, and there are students who are online. So I would like to. I'm using the visualizer, so I would like, some help. It's not connecting for some reason. Yeah, no, I'm using the standard PC, not the laptop. Thank you very much. Thank you. Bye. 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 Bye.
Yeah, where?
So now they can hear me, but they can't see. Someone just said, we can hear you now, but we just can't see. Oh, dear. Hello. Yeah, basically, I've got some students on Teams.
Oh,
Yeah.
right, okay.
And what I'm trying to do, I'm trying to use the visualizer,
Right.
and so they can see. They can see. I did it in the past. I don't know why it's not working now. Why is the camera not working when
Yeah,
you go
you
here?
can share your screen, can't you? So it's
Yes,
not.
I go here. Look, if I go to Teams and share screen, okay, sharing, it doesn't. It's not.
No,
See what I mean? I can have my PowerPoint, but I can't have. I don't know.
Yeah, because usually visualize just goes to the system. It doesn't go to the screen.
Yeah, but I used to do
So-
it through this. I used to do it through here. You go to camera. So why it's
Yeah,
not?
all right.
Why it's
That's only that camera. That'll only be that. That won't show up on the desktop at all. You see.
Oh, really?
Yeah. So you could kind of do
But
it.
even that is not working.
No, you could do it through that if that was. Yeah, I don't know what's going on there. Oh, it's bloody learning. Nothing seems to work.
No.
It really doesn't. Isn't that working? At least we can get that working. Yeah, it's don't see it at all, is it? 'Cause that's the. You've got the main camera there. That's that one there.
Okay, yeah.
And then you've got your. So if I go camera here. I'll do camera. It's just that. That should.
That's the
with
same,
that.
isn't it? Yeah.
Yeah.
Oh, no.
Just give us that. I don't know which one it is. Is that? Goes in there. Oh, this one's next to you now. I'm sure there's a camera in there. Back, isn't it? Did you use the webcam before today?
Not in this room. I've used it in ECB, no problem, in the same way, but it's just here in this room.
You've not used the actual visualizer, have you?
The visualizer at the moment is projecting there.
Yeah, it'll do that. But when you've got it working, it's always been with the webcam. It's not been with that asset.
And also, I don't know why it's a blue background anyway.
I don't. It's just the lighting and stuff.
Is it?
I mean, you can't see it from there, can you? Just thinking, if you go into
the problem
does
is
that share anything?
share.
So if I go into the actual app there, if I just grab the mouse.
You see, you can share the camera, but it's just not.
Yeah,
working.
but that would just you'd have to point it down.
It's okay as long as it doesn't. It's not even working.
Yeah, I'm just wondering with this, what this actually sees. Can we see?
Offline. What is this offline?
Because that's not working. That's what normally is the webcam app, I think. That's the actual that camera up there.
Is
So
it?
that's pointing at that. That doesn't seem to.
Yeah.
That's not working as well either. As if it's worth rebooting or something. You can't add anything now. It's all set up. It's just
all
set
set up,
offline.
isn't it?
Yeah.
Okay.
If it's worth, might be worth a restart and see if it. Because if that camera works, you might be able to see the screen there. And
Yeah, that's what I mean.
Screen, yeah. So if you just reboot the PC, it might. Because they play it as well. It's absolutely. It's just.
Yeah.
It's all been last minute installations that just don't work properly.
It doesn't. Yeah.
But yeah, if you just reboot the whole PC and then we'll just see.
Shall I try again?
Yeah, that should come up on the web. The web app should show that camera there.
Yeah.
So just reboot the whole system, come out of it. Yeah.
So here, sign out.
You can do.
Oh, here.
Yeah, we'll reboot the whole thing. Yeah, sign out. I think you have to sign out there, and then we can restart.
Can you hear me now? Oh, okay, they can hear me. Okay, what I'm going to do, change of plan. I'm not going to use the visualizer for today because he said they will look into it and fix it for next week. So I'm going to use the PowerPoint, not PowerPoint exactly, but the lecture notes that I have. So I'm going to share the screen. I hate teaching this module using PowerPoint, okay? Because it's one of these things where you need really to go through things and explain them. And the PowerPoint is good if you are teaching materials or some other topics, but not this one, okay? So anyway, I'm going to share the screen with you, okay, and go through the, so it is recording still. Right, so where is the, okay. Okay, now, so let's go through this now, please. If I can have your attention, please, because I'm going to explain this very, very slowly, and it's very important that you get a good understanding of the principle of the principle of the method. Okay. Okay, you're not sharing your screen, have I? Is it? Has it come through? Because I'm sharing it. Has it come through? No? Not yet? Oh. Why is nothing is working? It's showing me that it's sharing, so I don't know why you can't see it. Is anyone online as well? Is anyone logged in online as well on Teams? Can you see if the screen is being shared? Is the screen being shared? No? If you go to Teams and you join online, please, one of you maybe. I am sharing it. I honestly am sharing it. I don't know why it's not working. No? Anyone online? Here? No? It's not sharing. Oh, dear me. Dear me, dear me, dear me. Yeah, it says it's share. I mean, it's telling me it's sharing. So why not? Why it is not shown? I have no idea.
Hi, Masood. We can see you now, but you're muted.
Can you hear me now?
Yep.
Okay, we're getting there. We're getting there. We're getting there. So we have this, as I said, continuous beam. Now, this is an example of a statically indeterminate structure. Why is it statically indeterminate? Because in terms of reactions, how many reactions have we got here in total? How many at A? How many reactions at A? 3. How many at C? 3. So we have 3 and 3, 6. And when you have a support like this, you have 2 reactions potentially. So you have 6, 7, 8. Okay? So you have a total of 8 possible reactions. And there are only 3 equations of equilibrium, isn't it? We said sum of vertical forces 0, sum of horizontal forces 0, and sum of moments about A point equal to 0. So you have 8 minus 3. 8 is the total number of reactions, minus 3 equations of equilibrium, which gives 5. And therefore, this is a statically indeterminate structure of degree 5 to the 5th degree. The higher this number here, the higher the degree of redundancy, the more complex it will be to solve the structure by hand, by simply using equations of equilibrium, okay? So this number here is an indication of the complexity of the structure, all right? Typically, when you have a statically determinate structure, if the structure is statically determinate, what will be this number here? If the structure is statically determinate, what's the number here? What would be the number here? The degree of redundancy will be what?
3.
0. Do you agree? Everyone? Because you have 3 equations of equilibrium, you have 3 unknown reactions, so the difference is 0, right? So for a statically determinate structure, the degree of redundancy would be 0. Anything bigger than 0, that means your structure is indeterminate, and the higher is this number, the more complex is the structure. So this is a highly complex structure because you've got 5, the degree of redundancy is 5, okay? So because there are so many reactions to determine, right? So now we are going to use the moment distribution method to solve this problem, all right? And what I would like to do for this problem is actually to draw the bending moment diagram for this problem fully. So I'm going to explain the steps. I'm going to go really slowly, and please stop me at any stage if there is anything not clear. The first step that we, with this method, is to split the beam here, to split it up into beam-ended, fixed-ended beam elements. What are we meaning? What we mean here? We mean that you split the beam here in the middle, okay, at B. So you split it at B into 2 beam cases. So now we have AB, this one here. So when you split up the beam, the intermediate joint becomes fixed. Can you see here? So intermediate joints become fixed. And you have now fixed-ended beam elements. So we have AB with the 5 kilonewton per meter, and we have beam BC with the 40 kilonewtons in the middle. Okay, so that's the first thing. Then we are going to use the fixed and this handout is actually already in Aula. So if you want to write extra notes, that's up to you. Okay, but it's already there. So we use the table to obtain the fixed end moments, right? And the table, let me see if I can share if I can find the table and share it with you. Give me 1 minute, please. Have you seen the table I've shared with you on Aula? The fixed end moment table. Anyway, there is a table that gives you the moments at the joints here. Okay, for example, that's not what I want. Oh, dear me. Okay, sorry. It's oh, it's taking me back to it's catching up. It's catching. Okay. So now we have got the two beams here, AB and BC, and we determine the moments at the joints, which we call the fixed end moments, FEM. Okay. So we have a fixed and we have a moment at A. That's the fixed end moment AB. The first subscript here indicates the joint. So when we say FEM AB, we mean the fixed end moment at joint A. When we say fixed end moment BA, we are talking about the moment at B. Okay? So the moment at A is W minus WS square over 12. And the moment at B is WS square over 12. The minus and the plus means that the convention we use is that if the moment is anti-clockwise, it's negative. If the moment is clockwise, it's negative. Okay, so for example, at A here, the moment is going anti-clockwise. If you look at your table, the moment is anti-clockwise, so therefore it's minus WS square over 8. So that's from the table. So W is 5, the length is 4, the span is 4, so 4 square is 16, divided by 12, which gives minus 6.67. And similarly, the moment at B is plus 6.67, right? Then we do the same for member BC. The moment at B will be minus WL over 8, and the moment at C will be WL over 8, which gives, when you substitute W and L, it gives minus 20 and plus 20 respectively for the moments at B and C. Right? So I repeat, so this is the first step, okay? So the second step. So the first step, you have a continuous beam. The first step, you split it up into 2 or 3 if you have got a 3-span beam. So it splits up into fixed and the beam elements. And then for each beam element, you use the table and you determine the fixed end moments, the moments at the joints. And that's the second step here. The third step, okay, the third step, if we now try to reconnect, if I try now to put these two here, these two elements together, if I try to reconnect them, to reassemble the two elements here together to form the initial beam, what problem do we have? The problem we have is this now. Okay, look. So we have got this beam, AB, we have an anti-clockwise moment of 6.67, and we have a clockwise moment of 6.67, and then we have a moment at B of minus 20, anti-clockwise. Yes. Because it's fixed-ended. You have a beam here. It's not simply supported. It's fixed-ended. Can you see the difference? Yeah. We are using a table here. We are using the table. There is a table that I have uploaded onto. Let me see if I can show you the table here. Let me see if I can share with you the table. Okay, just one moment. No, it's not sharing the visualizer. That's the problem. Sorry about that. Yeah, I mean, this is the table on Aula. If you look at the table on Aula, that's a table. And it gives you the moments at the joints for each case, right? And all you have to do is basically use it. You don't have to learn memorize the moments by heart, okay? So use this. So this is from the table straight away, okay? Anyway, so if we take A, B, and BC and try to reassemble them back, put them back together, the problem we have now is that at B we have plus 667 on this side here on the left, and on the right we have at B we have minus 20. Can you see that? So we have 6.67, and then we have 20. And what's the problem with this? Not exactly, not balanced. Because remember, if you have a continuous beam, the moments, if you take an intermediate joint here, I go back here, you see, if the bending moment at B on the left and the bending moment at B on the right here must be balanced, must be in equilibrium, equal and opposite, okay? You must have equilibrium there, right? And therefore, what we have here is that when you try to reassemble the two beams back together, you have an out of balance here of minus 13.33, okay? 667, that's positive, minus 20, because it's anti-clockwise, which gives minus 13.33. So we have an out of balance here of 13.33. The out of balance should be what? Should be 0. Yeah? So the out of balance here, if the joint was in equilibrium, the out of balance here should be 0. But it's not. We have minus 13.33. So how much do we need to add to that to make it 0? Plus, isn't it? So I need to add plus 13.33. The minus 13.33 is called the out of balance, and the balancing moment is the opposite sign. Is that clear? This is how much you need in order to make joint B in equilibrium. That's the balancing moment. And now we need to find a way to actually getting rid of this moment. We need to get rid of this. And we can't just ignore it. We can't just, get rid of it by just ignoring it. We can't do that. So what we're going to do, we need to take this moment here and balance it and distribute it to the adjacent joints. Yeah? Okay? Is that clear? Yeah, I mean, imagine you have 3 people. You are 3 people, 1, 2, 3 people, and you are in the middle, and you've got so much load to carry. If you can't do it, what do? You give some, exactly, to the people next to you. Okay, so you say, take this and take this. So you share the load. And in this case, what was going to happen? That moment, this moment here, we are going to balance it and distribute it to the adjacent zone. How much do you give to each beam depends on the the rigidity or the flexibility of the bead. Okay, so that's what will decide how much we distribute to the other. So that's the next step. Okay, so the next step is to distribute the out of balance moment to the adjacent joints, and we do this by defining what we call the distribution factors. The distribution factors are the factors that will tell you how much each beam will take, how much each joint, how much each adjacent joint will take from the beams. Okay, and by definition, the distribution factor for a member IJ, if it's in general, I'm making this in general. I go back to A, B, and BC in a moment. Okay, so in general, the distribution factor is going to be equal to the stiffness of the member IJ divided by the sum of all members connected to joint I. Okay, the first subscript, remember this, the first subscript always refers to the joint in question. Okay, so I repeat, the distribution factor for member IJ will be the stiffness of IJ divided by the sum of the stiffness of all members connected to joint I. For example, if I substitute I by A and J by B, so that will be the stiffness of member AB divided by the sum of all members connected to joint A. If I substitute this by B, A, so distribution factor for BA, it will be stiffness of BA divided by stiffness of all members connected at B. How many members are connected to B? Yeah, I mean, look here. There is only one member connected to A, and there is only one member connected to C, but at B we have two members connected to B, isn't it? We have BA and BC. All right, so when you use that definition here, always remember that you are referring, again. So when you do that, always remember that you're referring, the first subscript in your definition is referring to the joint itself, okay? Okay, so that's the definition. And what is the definition of stiffness? The stiffness of a member is equal to EI divided by L. What is E? Yes, I, second moment of area, isn't it? About the neutral axis, or if you want, the moment of inertia, divided by L, that's the span of the beam. All right, so if you have a beam AB, the rigidity or the stiffness will be Young's modulus for that member times the second moment of area about the neutral axis divided by L. And this is usually given to you, okay? EI is usually given. I don't expect you to determine I at all, okay? It's always given to you, and you divide it by L. Right, so going back to our beam, this is our beam here, AB. Joint A is fixed, right? I mean, typically, imagine you've got a beam and it's fixed to the wall. Okay, so you have a wall on the left and the wall on the right here. So we have a wall here, and the beam is infinitely rigid, connected rigidly to the wall here and the wall there, and then it's supported in the middle. What could it be? What could it be? Yeah, it could be a column. You could have a beam, isn't it? You can have a continuous beam, and you have columns in between, isn't it? So the supports here could be, for example, a column. All right. So anyway, so I'm going to use this definition here. I'm going to use this definition there for each of the joints: joint A, joint B, and joint C. We have three joints. So I'm going to use it for all three. So starting with joint A, right? Look at the definition here. Starting with joint A, the distribution factor for AB, because we have only one member. Remember, joint A, we have one member connected to joint A, and that's member AB. So it will be stiffness of AB divided by the stiffness of all members connected to A. Now, stiffness of AB is EI, okay, that's given EI, divided by L, which is 4, divided by stiffness of all members connected to A. We have one member connected to A, and then on the left side we have the wall. So you have EI over 4 for this member here, plus the wall. Now, we assume that the wall is infinitely rigid, so we give it a rigidity of infinity. So it's very large, meaning it's very, very large, okay? So when you divide, if you divide something by a very large number, what do you get? Do you agree you get 0? Yeah, if you divide by infinity, something by infinity, you get 0, if it's very large, okay? Similarly now, for joint B, we have two members. We have a member BA and we have member BC. So we need to consider both. Okay, so now going back here, scrolling down, sorry, to joint B, we have two members. We have member BA, this one here, and we have member BC. For member BA, we have stiffness of BA, which is EI over L, which is 4, divided by the stiffness of all members connected to B. Members connected to B, we have EI over L over 4 for AB, plus EI over L, which is again 4 here for BC. It just happened that in this case, AB and BC have got the same span, but they could have different spans. Okay. Now, when you simplify the EI here, you have a quarter divided by a quarter plus a quarter, which gives half. The good thing is that EI will always cancel. Your distribution factor will always give you a value because EI will always just cancel, okay, as you can see here, right? So in the future, you could actually completely ignore the EI and say it's 1 over 4 and 1 over 4. So you have 1 over 4 divided by 1 over 4 plus 1 over 4, all right, because EI is going to cancel anyway. Similarly for BC, we have distribution factor for BC, stiffness of BC, which is EI over 4 divided by stiffness of all members connected to joint B. That's joint B here. So we have EI over 4 plus EI over 4 equals half. Are the distribution factors clear? Is it clear or not? The more you do, the more examples we do, you will see that then it becomes really very systematic and you can remember it. I know the first time you are trying to grasp the definition, but when you use it so many times, you find it easy. But are there any questions I can take here now? Anything at all? Okay, so finally for joint C, we have only one member connected to joint C, and that's member CB. So it's very similar to joint A, actually. So we have EI over 4, that's the stiffness of CB, divided the stiffness of CB plus the stiffness of the wall, which is infinity, okay? And that gives 0. So now we have the distribution factors for each joint. For joint A, we have 0. For joint B, we have two members at B, so it's half and half, and we have joint C, which is 0, right? And I don't want to give you more. How do you say it? I don't want to give you more to chew today. I want to leave something for next week. But what I would like to do now is actually get you to do some tutorial questions. You can work together if you want. Let me see if I can share again with you. Sorry about that. So give me a minute. I mean, we are supposed to do a lecture and a tutorial. So let me see if I... No questions on this? Okay, thank you. Where can I find the... No, not this one. Okay. Can I have your attention, please? Yes. Are you able to access your Aula and get the distribution table, please, everyone? Yes. Okay. Because otherwise, I don't know if there is a photocopier here. I can get some copies in the meantime. Okay. So what I would like you to do, please, can you, for the first example, for this first example here, can you work out, please, the fixed end moments? What are the moments at A and B? Right? I'm going to give you, for each question, I'm going to give you 2-3 minutes maximum, and then we move to the next one. Is that okay? Yeah. Who wants a copy of the handout? For the okay, I'll see if I can put the machine here. In the meantime, please try and do that. Okay?
Oh, was it? Yes.
Anyone? Any password?
Yes.
Anyone else? About 2 minutes. How many? 1 hour. Anyone else? Okay. Okay, so I mean for this example here, you are using which one in the handout in the table? First, second, third, which one? Exactly. So we're using the second one. If you look at the second equation, A is 2 meters and B is 4, right? So you substitute A by 2 meters, B by 4 meters, and L, the total span is 6 meters, okay? So you use those equations, and that should give you the fixed moment at A and at B. So you have minus W square, minus WAB square over A square at A, and you have plus, clockwise, WA square B over A square. All right? What answers do you get? 50 something, isn't it? 58 something, yes? Is that, did you all get, or is it 88? I don't know. I can check the answers. Sorry? Okay. Yeah, I can check it quickly. Yeah, so you should get for the first one, the answers are minus 88.89 and 44.4. Is that what you get, everyone? Yeah. Always put the units, kilonewtons per meters. Okay, let's look at now number 2. Happy with that? So let's look at number 2. So the second one is this one here. And what we have again a fixed-ended beam. This time we have a uniformly distributed load of 4 kilonewtons per meter. And we also have, on top of that, we have a concentrated load of 20 kilonewtons in the middle. The total span is 5 meters. All right? Which ones or which one you are using? We are using here from the table. Do you agree we are combining 1 and 3? Yeah. So you're combining. You calculate the moments at A and B with the 20 kilonewton only. Then you calculate the moments at A and B with the UDL only, and then you add them up together. Is that clear? And you use what we call the principle of superposition. So you will be superimposing the two together, okay? So you do it for 20, and then you do it for the 4, and then you combine them together. Okay? So basically, so at A, it will be minus WL over 8, okay? And then you have, for the UDL, you have minus WL squared over 12. And then you add them up together, plus. Is that clear? Yeah? And you do the same at B. In this particular case, because the load, the 20 is in the middle, we know that the moments at A and B will be equal and opposite. We have symmetry, isn't it? So you only need to do it for A, and then for B, it will be with a plus. So you have minus at A and plus at B equal opposite. Is that clear? And if I can show you the, has anyone done it? How many people have done the second one yet? Okay. Yeah, thank you. So let me see if I can show you the solution. Yeah, so this is the second one. So we use the principle of superposition. So you have the minus WR over 8, minus W squared over 12, which gives minus 2083. And then you do the same at joint B. You have WL over 8, 20 times 5 over 8. And then you have W, 4 times the span, 5 squared over 12, which gives 20.83. And you can see that the two are actually equal and opposite, which is what we said, because we have symmetry. Okay? So when you have a combination of loading, you may need to use more than one of the equations from the table. So if I give you two UDLs and 2-point loads, so you have to use the table, you have to use the equations from the table maybe for each individual case and then add them up together. It's not difficult. So wherever the complexity of the loading you have, it doesn't matter, because you can always use the the principle of superposition for any complex combination of loading. Is that clear? Okay, so let's go back and see if we can do the third, how many we can do in the remainder time. So number 3 now. So for number 3, you can see here we have got 2-point loads now. We have 2 concentrated loads. We have 30 kilonewtons at 2 meters from A, and we have also 30 kilonewtons at 2 meters from B, and the total span is 7 meters. So 3 meters between the two loads and 2 meters from either end, which gives a span of 6. Again here, which ones we're using? Number 2, how many times? Twice. So using number 2 twice. That was the that was the exam question which I've last semester, and a lot of people were thrown by this. Okay, although it's quite simple actually, but a lot of people struggle to figure out that you need to use the number 2 here twice. Okay, for the first case, for this 30 kilonewtons, A is 2 and B is 5, and then for this 30 kilonewton, A is 5 and B is 2. That's all. And then add them up together. Is that clear? And the reason I'm giving you all these examples just to show you that it doesn't matter what combination of loading you have, it's the same table. It's the same table. You can use it over and over again, whatever loading you have. That covers every possible combination you can think of. Is that clear? Yeah. So when you have a loading like this, don't think, oh my God, it's not in the table. It is there. You have just to use the principle of superposition for your particular load combination. So again, if I can reveal the answer, so solution, okay. This is number 3. So can you see here? We've used it twice. So you have got A and B interchanged, right? Which gives, not surprising at all, we've got minus 4286 and plus 4286 because the beam is symmetrical. Because the beam is, we have a symmetrical arrangement, so the moments at A and B will be equal and opposite sign, clockwise and anti-clockwise. Is that clear? Yeah. So again, watch out for this. I had students who used the equation correctly. They spotted that we have to combine, but they got the wrong answers, and they didn't realize that they have to be equal because of symmetry. Right? Okay, any questions? Okay, so let's carry on. I think we can do one more maybe. Please do stop me if there is anything not clear. Okay, now I think that's the last one, isn't it, for today? Yeah, okay. Now we have got this arrangement. This time, the beam is fixed at A, and we have a roller or a simple support at B, and we have a point load in the middle, you know, at 3 meters from A and B. Okay, and we're using which one? 1, 2, 3. Number 4. You agree? Yeah. Number 4. Is that clear? Okay, number 4. So in this case, we know that the moment at B is 0 because it's a simple support. So we have a roller here, so the moment at B is 0. And the moment at A, again, if you look at the table, we know it's going to be negative because it's anti-clockwise, okay? And the moment is minus, at A is minus WL square over 8. W is, sorry, I do apologize. I was looking at the wrong one. So it's minus 3WL over 16. Minus, so the moment at A here is minus 3WL over 16. W is 50. And L is 6. So when you substitute, you should get the answer minus 56.25. There are tables, you know, this table here, you can find, you find in any good structural analysis textbook. Any good textbook will have that table somewhere at the end of the book, okay? And some of them will give you a more extensive list of all other possible cases. These are the cases that we are going to deal here with, you know, so I don't want to give you the whole thing, but you can imagine, I mean, for example, if you have got a combination where you've got moments, for example, at a particular location, that's not covered here, where you have an external moment, right? So there are cases not covered in this table, but it does cover what we need for our own purpose. Is that clear? Okay. Any questions? It's 10:02. Any questions at all? Yeah. I'm really sorry. I can only apologize about the you know, the bad start with the IT issues that we had. The good thing is that I have already uploaded the pre-recorded session, which covers exactly what I've done today. Have you managed to watch it? Yeah. So there will always be a pre-recorded session, and then the good thing, as I said, if things go wrong, at least we have got a recording. Thank you very much. See you next week. Thank you.